So on the first day of class, we had this discussion on what is a particle. So the official definition of what is a particle is something that has no size, but it has mass. Now, obviously, physically, that's not possible. Everything has a size. So basically, a particle in this class means a dot. Well, as we talked about in class, that dot looks like a dot. But baseball, when you look at it from the stands, it looks like a dot, even though, it's like about 3.5 inches in diameter. So for this class, the practical application of this is no matter how big something is, as long as all the forces go through one point, we'll consider it a particle. So we had this problem earlier with a gusset plate, and there was some kind of force like that. Some kind of force like this, some kind of force like that, and another force here. So obviously this thing has a dimension, but when you take all these forces, they all go through that one point there, and so this will be equilibrium of a particle. We can consider all those forces going through a point, and we can analyze it as if it was a particle. So when all the forces go through a single point, this is an important phrase you need to remember. We say the forces are concurrent, or that these are concurrent forces. So you're going to just have to somehow memorize that concurrent means they all are going through the same point. So I just Googled the definition of concurrent, and so in normal English, concurrent means existing, happening, or done all at the same time. However, it says in mathematics, it means 3 or more lines meeting at or tending toward one point. So this is a mathematical definition. Lines are vectors, so these force vectors or lines are all meeting at one point. Obviously, two vectors will either be parallel or concurrent. They'll intersect somewhere. It's when you have 3 or more that it's unusual for them to be all at the same point. So this is kind of a unique thing. Why are we learning this? So first of all, you start with this because equilibrium of a rigid body built on this, but it actually does really happen in real life. So where do concurrent forces occur? Okay, strings tied to a ring. So if you have a ring like this and then you have strings pulling on it, those strings will slide around so that they always point towards the center. That will be concurrent. Cables around frictionless pulleys. We'll do lots of cable problems in this class. So there you have that pulling, and the cable, has some kind of hoop on it that you hang from the ceiling or something. Those forces will all be concurrent. Okay, hooks from cranes. Those forces are all concurrent. So you have a crane hook. It's being pulled up, and whatever it's pulling will slide down to right under there. It'll be concurrent. Okay? Or if you're picking something up with a hook with 2 cables like this, and that goes to like a beam that you're holding, these 3 forces are always concurrent. Anything hanging from a cable will be concurrent. So you have a cable like this, and then you're hanging something from it. These forces will be concurrent. And finally, joints of a truss. So you've all seen bridges that kind of look like this. We'll analyze these in a few weeks. Right here, all the forces are concurrent. And actually, this little thing up here, that's physically what a joint of a truss looks like. When you draw it on paper, you just draw a dot with lines coming out of it. But physically, it'll look something like this drawing up here. And speaking of things hanging from a cable, we'll take a little side detour here, and I'll explain to you something that Robert Hooke said. So Robert Hooke, he's famous for Hooke's Law, but he also said As the cable hangs, the arch should stand. What this means is that if you took a clothesline and you hung a weight from it, you know, that's gonna sag like this. If you were to make a bridge, it should stand the opposite of that. So you flip it over, and then this would be the ideal shape for the bridge. So let's try another one. So if you had a cable like this, and you had two weights on it, so let me draw two weights here. So there's that and that. So you have to be able to visualize how that would sag. And so how that would sag would be like this. Okay. If you were to flip that over, that would be the ideal shape for a bridge where you had two equal loads like this. Okay? And so I use this a lot when I enter bridge building contests. So when you enter these bridge building contests, you're given a limited number of popsicle sticks, barbecue skewers, spaghetti, or something like that, and you have to make the strongest bridge. Well, the best shape of the bridge is always how the cable hangs. So if in the contest they're only loading it at the middle, it should look like this. If in the contest they're loading it at 2 points, it should look like this. And if you were ever in high school, they say stuff like triangles are the most stable shape. That's true, but the optimum shape are these shapes, and they have a fancy name. They're called funicular curves. So what if you have a clothesline and you put lots of weights on it, like lots of cars or something, but let's say you have lots of weights hanging from the clothesline, or just actually the weight of the clothesline itself, that will sag like a parabola. And so the ideal bridge shape when you have lots of things on it distributed all the way across is this parabola. And so if that contest was to distribute it like that, this is the correct shape, and you see bridges like this all the time. That's because there's lots of cars on the bridge like this. But for a spaghetti bridge contest, you need to optimize your design for the actual loading of the competition. And so anyway, as the cable hangs, so the arch should stand. But for this class, what we're interested in is like, oh, let's look at this joint here. How much tension is in the string, and so that free body diagram, let's practice. So everything in there is just the little dot with the dot right there. I'll draw that a little big, and then you got that string coming out, that string coming out, and that weight. Then draw everything in there. So I've got that weight in there. We'll draw that. There's the weight W, and we've cut through this string. We call it tension 1, and we've cut through that string, tension 2. So that would be the free body diagram of that point right there. Okay, so back to what we were doing earlier. So this is a summary of the procedure for solving 2D particle equilibrium problems. Step 1, draw the free body diagram. Once you have the correct free body diagram, look at everything in the X and set up some of the X forces equal to 0, and look at everything in the Y and set up some of the Y forces equal to 0. So I promise there will always be only two unknowns. You have two equations, you can solve for the two unknowns. What we're going to do is pause here, and the next video I'll do 4 examples, or I think 6 examples.